Scientists worry a lot about the measurements that they make because this can have a crucial effect on the success of an experiment. John has decided that he needs to lose some weight, and to do so he's going to follow a new diet. However, he isn't convinced that the diet will work. So John decides to measure his weight before he starts the diet, follow the diet for 2 weeks, and then measure his weight again after the diet. Now John knows that his weight can change during the day, for example before and after eating, exercising and so on. And so he decides to measure his weight 3 times during the day before the diet and 3 times during the day after the diet. Before the diet, he found that he weighed 93.9, 94.0 and 94.1 kilograms. So those numbers are very close together and they come out at an average of 94 kilograms. After the diet, the measurements he took were 91.9, 92.0 and 92.1. Again, those measurements are very close together with an average of 92 kilograms. It certainly looks as if John has lost some weight, around 2 kilograms. All of the readings of his weight on each day are quite close together. We could say that the data on each day aren't very scattered because all of the measurements on each day are quite close together. They are all within 0.1 kilograms of the average. The scatter of the data is quite small, and there's a noticeable difference between the average readings before and after the diet, so John can be reasonably confident that the weight loss is real. But now imagine his results looked like this instead. Before the diet, his weight was measured as 93, 94 and 95 kilograms on each of the occasions during the day when he measured his weight. So that comes out at an average of 94 kilograms. And after the diet, he measured his weight as 91, 92 and 93 kilograms. Again, that comes out as an average of 92 kilograms. This time, although the averages are the same as in the previous experiment, the results on each day are much more scattered. The individual readings are 1 kilogram away from the averages on each day. Can John still be sure he's lost some weight? In fact, one of the readings before the diet was 93 kilograms, and one of the readings after the diet was also 93 kilograms. So if you looked at these figures alone, you might think the diet hadn't worked. So it's harder for John to tell if he's really lost weight when the results are more scattered, less consistent if you like. So when we look at scientific results, we have to look at the values themselves as well as the scatter of the data. So how can we tell if two sets of numbers really are different? In this case, did John really lose weight? Well, if the difference between the averages is large and the scatter of the data is small, it might be obvious. But in other cases, scientists have to resort to statistical tests to look at how big the difference is between the averages and how scattered the data is. The statistics allow us to calculate a probability, called P, that in this case will tell us whether the change in John's rate is a real difference rather than a difference that came about by pure chance because the data was so scattered. We might write this as P is less than 0.05, which means that the probability is less than 5% that the difference we observed came about by chance. One way that might be easier to think about this is that if we conclude the difference in John's weight is real, then if P is less than 0.05, then there is a less than a 5% chance that we are wrong in concluding there's a real difference. Scientists make a distinction between precision and accuracy. Precise results are ones where all the readings of the same thing are quite close together. In contrast, accurate results are ones where the readings are close to the true value that we're trying to measure. So results can be precise but inaccurate if all the measurements are very close together but a long way from the true value. Scientists often report their results with an estimate of the scatter of the data, and they sometimes refer to this as the error, although it's more properly called the variance. The larger the so-called error, the more scattered the data, and the less confidence we can have in any average value that's quoted from that. So what else can scientists do if the difference between two groups is quite small, or if the data is quite scattered? Well, probably the best solution is to improve the precision of our experiments, but that's not always possible. Another solution is to test lots of samples. This increases the power of the statistics. By testing more samples, it's easier to detect small differences. This has real-world implications that affect all of us. For example, if a pharmaceutical company is testing a new drug, but it's anticipated that the data will be very scattered, then the drug has to be tested in lots of patients before we can be sure that any effect of the drug is real. But if the drug is tested in lots of patients, that makes the cost of testing the drug much higher, and consequently that means we end up paying more for the drug. So an apparently mundane subject can affect how much we end up paying for drug and therefore whether it's used or not.